Welcome to episode 3 of the Heights of Humanity podcast. In this episode, I sit down with Dr. Edward Marshall. Dr. Marshall is a geoscientist specializing in isotope geochemistry and igneous petrology who is currently working as a postdoctoral fellow at the University of Iceland. If you've ever seen videos of scientists in Iceland going out to a volcano and collecting lava samples, odds are that was a video of Dr. Marshall. While arguably less flashy than his fieldwork, his geochemical expertise provides extremely valuable insight into the origin of magma deep below the Earth's surface. His work is vitally important in better understanding our Earth's crust and mantle, as well as volcanic eruptions on the surface. Expect to hear about learning from past mistakes, what it's like to be up close and personal with a volcano, the recent Grindavik eruption scare, and more. Now, without further ado, and we are live.
Cool.
Dr. Marshall, thank you for coming on. I really appreciate it.
No
Thanks for taking the
problem.
time.
No problem. Thanks for having me, Jason.
Yeah. I know for me, it's been an exhausting week. I'm sure you've had an exhausting week as well. So yeah, thank you very much.
Yeah, no problem. The conference has been really good, and I've seen a lot of cool stuff.
Yeah.
As we were saying before, there's not like a huge amount of high temperature geochemistry, which is what my background is in, but still got to meet a lot of old friends and catch up and see the UT people. That's always great. Yeah.
So I'm going to start off by asking a question that I ask a lot on this podcast, and it's kind of a big question. It's pretty philosophical, so be prepared. What does success mean to you? When you're striving for success in your life right now, what are you striving for?
Wow, that is pretty philosophical. That is a good question. I mean, I think we all have various goals we want to achieve.
Mm-hmm.
It's not like I'm not so simple that I have one goal that I'm working towards. So it's kind of a list. I have a family. My goal is to keep my family happy. I have a career. I want to be successful in my career. I have, personal interest in geology. And so it's not actually, in some ways, my career isn't actually connected to my interest in geology. If I got fired from my job, I'd still be, or if something happened and I wasn't in geology anymore, I'd still be very interested in pursuing it in some way.
Mm-hmm.
And so success for me really, really amounts to like, am I able to kind of pursue my goals? Am I able to kind of like set goals and have the satisfaction of pursuing them? And and connected to that sounds very unemotional, but part of this is also the immense like gratifying and frustrating part of having a family. My son is 1.5 years old, and I'm at this conference pursuing one of my goals.
Yeah.
And while I'm here, it's difficult to be away. But then I will get to go home and hug my son and feel good about things and feel like, I get to be there for him and kind of feel like I'm a successful family man in that moment.
Yeah.
Yeah.
It's almost this like delayed gratification aspect of like, you're at this conference and you're missing your son and you're working hard in this area, and then you go back and it's like even more satisfying. Is that accurate?
Yeah, I think it's more like, yeah, I think that's pretty accurate. I just I guess to pursue, there's what's the term? There's to pursue any goal means you're not pursuing all goals at once. You can't do everything at one time.
Yeah.
So there's always an opportunity cost for the pursuit of any individual goal, and you have to focus to do anything difficult. So but that's life. Coming to the conference to like be geology ed and be able to really embrace that sets me away from my family. And then when I go and I really participate in being a family, and I've been on actually parental leave much of this year. I'm not pursuing my geology goals as hard as I would want. So this is life. It's like, you can't get everything you want in every instant. But, if you play it smart, you can push a lot of different things all the time.
Yeah.
So for me, it's about like making steady progress. I guess if we were to wrap it all in a ball, success is, making steady progress on all the fronts that you care about. Because if you sacrifice everything for one, you end up with regret.
Yeah.
You end up with, I've pursued geology, but now I'm, you have like some bleak outlook. Like even though you wanted a family, you've exceeded enormously in geology, but you aren't married. You don't have a family. You never did much dating. And you never really pursued that side of life. And some people do that. But I personally feel that I'm a fairly balanced person. I certainly don't have all my goal eggs in one basket.
Yep.
That's why currently I find myself hopping from place to place. So I did my PhD at UT, and then I moved to Iceland, which pursued two goals at once. So I moved in with my then girlfriend, now wife. But at the same time, I became a postdoc studying Icelandic basalts, which was immensely interesting. And so I was really fortunate to be able to kind of do two things at once. Recently, though, I moved to Germany, and this is the first time I've really had to kind of choose between kind of like my goals in life. So the move to Germany is really like prioritizing family. But now that I have a son, this is an easier choice than it might seem. And so right now I'm trying to kind of reestablish in Germany and work with a research group there and get some grants. I'm putting out grant applications. And we'll see how everything goes. But again, that's life. We never know where things are going to go. That's part of the fun, part of the scary thing, I guess.
That's amazing.
Yeah.
I heard this saying on a podcast a while back, and this guy was explaining this story about how he was in a bar and he was talking to someone older than him, and the older guy went, "Life is all about picking your regrets." And like I could really draw a parallel with what you're saying with that saying, because it's like every choice has opportunity costs. Like there's always you're always gonna have an amount of regret, and it's just about choosing the decisions that give you the least amount. Because if I could do A, or I could do B, right? And it's like, but like if I do B, then I'm gonna be thinking, man, I could have done A.
Right.
But if I do A, then I'm gonna be thinking, man,
Sure,
I could have done B.
right.
You just have to think.
It's opportunity cost.
Yeah.
So
So what was your initial motivation to pursue geoscience?
Well, I don't even really remember. I was too young. I've always been interested in geology.
So since you were like a young kid?
Since before I was a kid. Like I have when I was 4, I have a big geology book that I have, and inscribed on the inside is the story from my parents about the book, which is that I was released into Borders bookstore, R.I.P. Borders bookstore, for people who remember Borders. But so I was released into Borders bookstore and allowed to kind of wander around and find whatever book I wanted to buy. And I ended up buying this National Geographic, lots of pictures, lots of cool stuff in it, but all about volcanoes and plate boundaries and kind of the geology of really volcanoes, everything about it. And I loved this book, and I still have this book actually. I took it all the way with me to grad school in Iceland and now Germany. It's kind of like a personal touchstone back to the beginning of it. And it's awesome. It's really well written and stuff, so I still look into it sometimes. So I'm kind of a weirdo in geology. A lot of people find geology along the way, or through random classes that they're forced to take or random people they meet or experiences they have. And I was just immediately attracted to geology for some reason that I can't explain or understand.
Mm-hmm.
And I've always been really attracted to it. And I think part of this is that my family are kind of all natural scientists in their own way.
Mm-hmm.
So like my father and my grandfather were very into birding, kind of like the hobby of going and counting birds and
Mm-hmm.
seeing as many different bird species as they can find, and kind of like honing the craft of like being able to identify birds in all sorts of different settings. Oh, I can only hear the bird, but I can identify by call. I can identify by silhouette. I can identify by body language.
Mm-hmm.
These types of things, and you kind of become an encyclopedia of everything birds, and
Mm-hmm.
it was kind of natural for me to take this kind of passion and apply it to rocks. So I think like the nice thing about being in my family is I got to see so much passion for the natural world,
Mm-hmm.
and I guess that must have gotten me excited at an age so young that I can't even really remember.
Yeah.
Not being excited about mica, for example. I remember my grandfather like showing me, Edward, this is mica, in his like old timey grandpa accent. I'm still interested in it. Like my relationship with geology has changed. I'm a grown ass man. I'm not a little kid anymore.
Yeah,
But
yeah, for sure.
I have you go through life and you collect dents and get beat up a little bit. So it's not the same kind of like naive passion it used to be.
Mm-hmm.
But it's still a lot of fun, and I still feel a weird magnetic attraction to the field
Mm-hmm.
that I can't shake. So yeah, I I just feel a deep connection to it, I guess.
Yeah, I can testify from my experience. When I was in high school, I actually really wanted to do exactly what you do. Like, I
Oh
would
yeah,
watch Volcanologist, take hand samples, and I thought it was like super cool, and it was the wildest job I can think of. But I definitely had doubts of like, is this the right path to go down? Like, am I going to make enough money? Like, do I really want to go to like that much school and get a PhD? Like, um, but I had a lot of mentors and people around me that were very supportive of me just going out and pursuing my dreams, which really helped me and is why it, yeah, it's why I am where I am now. So I want to ask you, did you always have just like no doubt that geology was what you wanted to do and you were always passionate about this, or did it kind of waver over time?
I I've had a complicated relationship with geology. Although I just told you that I told you that I collect kind of we collect dents and dings as we go through life, but um, maybe because I jumped into it at a really young age and very naively, I ended up in professional settings pretty frequently, way beyond my level of maturity,
Mm-hmm.
which caused friction between between me and a lot of other people. So I think a really good example. Well, let me take a step back. Like when I was a kid, geology was one option in the world, and for a while, I was also really interested in nuclear physics.
Okay.
I was really interested in the physics of nuclear weapons, and that was really my dad has a PhD in physics, so
Gotcha.
he had these books lying around way beyond in way greater complexity than I could hope to understand as a kid.
Mm-hmm.
But it was inspiring to kind of look through them and see like the graphs and pictures and things in the book and try to imagine what was happening and these kinds of things. But no, quickly, that was kind of a phase, and I went back to geology quite quickly. But a great story that's kind of very typical of my young self is that I was really excited about geology in high school. Very, very, almost obsessively excited about it. And my school had a program where um, you were kind of released from your obligation of school for a month in January.
Okay.
We called it, I forget what we called it, but in any case, you would go and you would find something to do for the January of your junior year. We called it the junior project. That's right. And so what I did is my aunt lived near University of Oregon. And so I went and I lived with my aunt, and I was able to somehow, I don't even remember, I think my parents probably assisted with helping me kind of interview with this person. But I was able to get kind of a unpaid job working in a lab with a geophysicist, who I will not name because later in the story he's very mean to me. But this is okay. He's a good guy. It was both of our faults. He took on a guy who was probably too young for the amount of responsibility, and I was an extremely irresponsible teenager. So essentially, in this January period that I was there living with my aunt working in this lab, I didn't have like very critical projects. I think I made movies in Google Earth to help out some of the physicists or the geophysicists' presentations. It wasn't very technical or anything. But he really liked me having around. I was helpful. And so he paid me to come back in the summer. This is where everything went wrong, of course. So I come back in the summer, and they wanted to give me more responsibility, which is probably a bad thing for a 17-year-old. And so they had me, they would give me seismometer receiver stacks, which is kind of where you have all the data from a bunch of seismometer stations, and you look at the arrivals of particular seismic waves, and you can, by manually kind of like interpreting this bunch of data, you can begin to interpret what's going on in the subsurface. Now, it's not very technical. You can literally train like a teenager to do it, which is what happened. But where it went wrong is that they offered to take me on a ocean cruise out to the Juan de Fuca Ridge off the coast of Washington State and Victoria and British Columbia. And this was a very maybe you'll go, maybe you'll not go. But somebody got sick on the boat and a spot opened up. And like, I guess the fallback person couldn't go. And so I happened in kind of this 1 in a million scenario that a 17-year-old ended up on this like very fancy ocean cruise. And I had a bunch of responsibilities on the boat. I was supposed to help take apart ocean bottom seismometers. I was needed to run a shift on the boat, which is where I kind of like looked at, this had a robot, so the robot would go down and snoop around. Down in the bottom of the sea, it would look at submarine hydrothermal fields. It was a very cool cruise,
like a marine, submersible.
Yeah, no, okay. Well, it was an undersea robot. So so nobody was inside the submersible, but it was running around on the seafloor, and it would collect samples, and it would take a lot of video, and basically I sat in front of the camera and took a picture. A fish would go by, and they would say, "Okay, take a picture." And so basically, if anything interesting happened, I would be on the picture button, and I would take a picture. And it was an 8-hour-long shift. It was not so hard. But the trouble was actually my third job on the boat, which was I was supposed to take video for this guy I was working with, so he could kind of like make a video and show it to people, I guess. And basically, I think this was probably too many jobs and too much responsibility for a 17-year-old. And yet, at the same time, was also not enough responsibility because it was kind of boring. It was 2 weeks out at sea, and I had an 8-hour shift, and every once in a while, we'd bring up an ocean bottom seismometer, and there wouldn't be stuff happening all the time from my perspective. And so, it was pretty easy to kind of shirk responsibility after a while. So things kind of came to a head. I wasn't really doing the things that were going wrong. Is I forgot to bring an alarm clock. So I would wake up late for my 8-hour shift sometime, which began at 8 a.m. And this made everybody very angry, or at least it made the scientist I was working with very angry.
Yeah,
And
boats are boats particularly um, particularly intense or serious about being on time and
yes,
things like that. Yeah.
yes, you have to be on time. There's kind of you need to behave professionally when you're on the boat.
Okay.
It's very important. Um, I think kind of the view is that even on this was a very large boat. This was the Thomas G. Thompson, which is a research vessel operated by the University of Washington. It's a very large boat. It can hold it sleeps many tens of people. Um, it can be out in the ocean and it doesn't even rock that much. It's a very large vessel. But And so because it's this big professional thing, we're spending hundreds of thousands of dollars a day to be out on the boat. Kind of you need to behave in a very professional capacity. And this is where having a teenager on board probably wasn't such a good idea.
Yeah.
So it's hard when you're 17 to behave in a professional capacity. And so I was, after 2 weeks on the boat, I was kind of crabby and snippy and I probably wanted to go home, but it was also an amazing experience. Every day I was seeing just incredible things, and it was a really truly incredible experience. And the people on the boat were really cool too, so I was having a nice time. But I would show up late, and I wasn't taking very much video for this geophysicist, and so he had basically had enough with me, and it all came to a head. I think we had an argument because I hadn't put cables away that I should, and then I behaved like a teenager would when you are nagging them about not putting the cables away properly, and I ended up like talking back and getting fired basically on the boat. The threat was like, oh, when we get back to land, like, you're out of here.
Mm-hmm.
And that's what happened. I stopped. He fired me, and I ended up. I was still in Oregon. I ended up working for his wife, who took pity on me because she was like, "Well, I think he treated you a bit too harshly, given that you're 17 years old."
Yeah, yeah.
And so I ended up working for her, basically doing the same thing, working on these seismometer receiver stacks. But this is a really hard experience for me. I think keeping things age appropriate is kind of important because you can put yourself in a position where you're really excited and you're really interested, but just because you're so young,
Mm-hmm.
you can't really, channel your excitement into responsible behavior,
Yep.
like focused and interested. Or at least I wasn't able to. And so, I think it would have been a much better experience if I had been a bit older. But because of this, it kind of tempered my, I wouldn't say, it was a moment where I grew up more. It was one of these periods in life where, bad things happen and you realize that, you have to kind of shape up a little bit. And so this was a moment where I shaped up a little bit and
Mm-hmm.
I learned some lessons. And so this is like a classic example of me as a younger person, just, I'm very excited. I'm following my passion, but I make some big mistakes.
Mm-hmm.
And I would say I continued making pretty big mistakes as a young person until something like my second year of grad school or something. It pretty slowly came together for me. Maybe I have attention deficit disorder, like many scientists. There's something about science that attracts people who like to hyper focus into it. But maybe because of this, it was difficult as somebody riddled with attention deficit disorder to kind of behave in a professional manner, even when I really wanted to.
Yeah.
It was tricky. But thankfully, sometime in the middle of grad school, in the middle of my 20s, it got a lot easier. So finally, the point of that is finally, I was able to kind of take my passions and channel them in a way that really interfaced well with my surroundings. And so I was able to finally like perform at a level that I wanted myself to perform.
Mm-hmm.
Yeah. So yeah, not always rainbows and yeah, rainbows and flowers. Even when you have really clear and directed passions towards something that you want to do.
Yeah.
You know, sometimes self sabotage just comes. Yeah, I don't know.
Yeah, I talked to my dad about something kind of similar to that, just like making mistakes as you grow up. And I kind of came to the conclusion that you have you have to make the mistakes that you make in life because you never would have learned that lesson without it.
Yeah,
So you could go on being a better person, but only because you made that mistake.
yeah,
So it's like, why, it's like, why beat myself up about it? I had to do this in order to get where I am now.
right.
And it seems like it sounds derogatory for me to call you a product of mistakes. It just seems like a wrong thing to say, but in a very positive sense. Like it seems like you make a mistake, but then you learn from it.
Right.
You didn't beat yourself up about it. You're like, okay, I got to grow up. Like I got to temper myself a little.
Right. Well, we're not perfect.
Yeah.
I mean, I'm not. I'm human, and I totally agree with you. I think as a young person, I'm a young parent right now, so I'm thinking a lot about myself as a young person because I'm imagining my son through kind of the same lens that I imagined myself, for good and for bad. I think my son is a totally different person than I was, but I look at him and I just see myself. So I can't help but make these comparisons. But one thing that I was really lucky is I understand we're coming up with these new terms like helicopter parenting, where the helicopter parent is kind of making sure that everything works right, or the bulldozer parent who removes obstacles from the front of their children. I'm very lucky that I had parents who, not only weren't doing that, but were throwing me to the wolves. They were like, "Oh, you like geology? Why don't you go work with a geophysicist?" Just basically throwing me immediately into the deep end, which I now realize is essentially what they were doing. And yeah, I made colossal mistakes.
Yeah, I mean, being 17 on a research vessel is wild.
Yeah.
That is
I
crazy.
I was by far the youngest person on that boat by a solid 5 years at least.
Yeah.
The next oldest person was probably the youngest graduate student.
Mm-hmm.
So there was a immense gap in maturity between me and pretty much everybody else on the boat.
Yeah.
But people liked me because I was young and passionate and interested, and I would talk. I wouldn't understand necessarily, but I would be like, "Whoa, what are you doing? What is going on here?" I'd talk to the grad students about their work. I'd talk to, I would talk to the senior researchers about what was important on the cruise, like why were we even out here? Like I had a pretty tenuous understanding of what was going on around. I mean, I'm 17. I've read a lot of geology books, but that's a pretty big leap to understanding exactly why we're going on this cruise and exactly what is happening and what the goals of the cruise are.
Huge leap, yeah.
Yeah, exactly. So, so I think it is. I think it's good that I had the experiences that I did. I think I wish I was older when I had them. I think there's kind of two ways you grow up. One is by having these types of experiences where, you have experiences and you grow from your experiences. But when you're young, you can grow just by your brain maturing. And I think, by just essentially development, just by mental development over time. And I think that I needed a little bit more of that. I think it's probably, I enjoyed my experience. I'm a product of my experience, but I do think that that age appropriate experiences are also good.
Mm-hmm.
I probably should have stayed on land on that one. Although I loved that I could be there.
Yeah.
It was incredible. I don't regret it. But maybe everybody else or certainly the geophysicist who sent me in there probably regrets it.
Yeah. I mean, I don't know. Yeah, it's like, for me, it's like, maybe if I were in your shoes, it's like, maybe, yeah, I would stay on land. But then also, maybe you would have made the same mistake somewhere else farther down the line, maybe because
That's
you
true.
didn't learn that lesson, you know.
That's true.
So who can really say?
I mean, I think everybody needs to be fired at some point.
Uh-huh.
And, everybody needs to have, and rightfully fired, not like bullshit fired.
Yeah.
Like they fucked up and they get fired so that they know where their limits are.
Yeah.
And so from that perspective, I think it was probably a good experience. I just, I guess my regret in all of that is just because I got fucking fired.
Yeah.
Nobody likes to be fired. I wish I made a better impression.
Yeah.
But that's life, I guess.
Well, look at you now, PhD on 60 Minutes twice.
Yeah. Well, everybody grows up too. So,
Oh, yeah.
Yeah.
So from that kind of initial interest in geoscience and then through the lessons you learned and then going through undergrad and all of that, how did you end up in volcanology specifically? What drove you to studying volcanoes?
Oh, not only when I was a kid did I know I wanted to do geology. I knew I wanted to specifically work on lavas and volcanoes and this type of thing. I didn't necessarily know exactly what I wanted to do, but there are many different approaches into that world. When I was in college, I did a study abroad in New Zealand, and I was able to take a physical volcanology class and do some volcanology fieldwork, and I realized very quickly that wasn't for me.
Yeah.
I wasn't. I'll put this in terms that I think are fair. I wasn't interested in the questions the volcanologists were thinking about.
What kind of?
So volcanologists were thinking a lot about how do certain volcanic processes happen? Why was an eruption as big as it was? This type of thing. And I realized that that wasn't the part that I was really interested in because, it wasn't grabbing me. It became very mapping lava flows going downhill. The intellectual part of it just wasn't it wasn't enough of a puzzle that I was interested in solving. And what I liked a lot more was things that have a lot more mystery, things that are a lot less tangible, actually, things that are more uncertain and more abstract. And it turned out that I really liked going deeper into the Earth because there was so much less understood and it was so much more alien. And so I really liked looking at the deeper parts of magmatic systems. I really liked thinking about the mantle because it was, we cannot visit the mantle. And so even though it's the volumetrically largest part, like the greatest, the part of the Earth, the largest part of the Earth by mass is the mantle. I mean, it's a really essential part of the Earth, and we know very little about it. Even today, there are still very fundamental questions that we're still trying to answer. It's like the root of volcanism. When physical volcanologists are talking about volcanism, they're really talking about volcanic phenomena, talking about how do and why do eruptions happen. And what I was thinking and interested more in is where does the magma even come from? What happens to it? That was magical. And I'll tell you, the first time I saw lava in person is in Iceland in 2021 at Fagradalsfjall. And it was a really cathartic moment in my life because I realized before you see something in reality, you've seen it on TV, you've heard people talk about it, but until you see it, there's kind of this, but is it really real? You haven't seen it.
Mm-hmm.
Maybe it's just kind of some story. And, you see it in real life and you're like, oh my God, kind of all the things I've been working toward have meaning. And it makes what you do so much more meaningful. And it kind of colors in the spaces in kind of your motivation, if that makes sense. So going and working on Fagradalsfjall, these series of eruptions in Iceland, and being able to really participate in sampling and in the research of those eruptions was really satisfying and motivating for me.
Yeah, I have that same feeling with the work that I do with the polar geophysics,
Mm-hmm.
because like I haven't been in there long enough to do field work, and everything is under thousands of meters of ice,
Right.
and it's you definitely get that sense of like, is this really real? Like you know it's real, but
Mhm.
it's like I understand that feeling like
Right.
perfectly. It's just like, like it seems very alien and far away. So
Mhm.
I would imagine getting so close to it. Yeah, that would be
But one
an
day,
amazing experience.
I'm sure you'll have the opportunity, if you continue down this line of research.
Mm-hmm.
You know, you've just started. You have plenty of time to change your mind, right?
Yeah, for sure.
But you know, one day you'll be able to go and stand on the top of the Greenland ice cap, or go to Antarctica and
Yeah.
really see it, and just see like these incredibly massive, huge ice caps, and how really, like, even though they're just one unit of ice, they're like a substantial portion of like all water on Earth, and it's just incredible to see. Particularly, obviously, fresh water.
Mm-hmm.
So, yeah, I do hope you get that experience.
Yeah, that would be cool. I hope
Yeah.
so too. We'll see. Yeah, you mentioned that going to seeing lava for the first time was very cathartic. How exactly were you feeling? Was it just like this? Well, you said it was coloring in the spaces, I guess the white spaces, and kind of your research and
Yeah,
things
yeah.
like that. How were you feeling then, and then how did like the way that you approach things kind of change over time? Like, did you have a newfound motivation to keep studying what you're doing?
Yes, I think when I did my PhD on mantle xenoliths, it was mantle xenoliths are portions of Earth's mantle brought up in lavas. It's very kind of a theoretical and abstract line of work, because you can't ever go to the mantle. These chunks of rock come up, but they're like fist-sized pieces of rock. And then when I went to Iceland, I had the this lovely opportunity to work on lavas, but it was like the feelings were lurking inside of me when Fagradalsfjall began to rumble. It was a very exciting thing, but because I had never experienced a volcanic eruption before, I didn't really connect that it could really actually lead to an eruption in like this internal way, like in an emotional internal way. Before we see things
Mhm.
for the first time, it's a little hard to take them seriously.
Yeah.
I don't know. In the same kind of way, like, if there's a big difference in how, let's say you live in a city and there's crime in the city, but the difference between somebody who has been robbed and somebody who hasn't been robbed is like a very different emotional space.
Oh yeah, yeah.
And in the same way, and that's kind of a weird analogy, but in the same way, there's a big emotional difference between somebody who has like lived through a volcanic eruption and experienced the volcanic eruption, and then it kind of being like this abstract thing you learned about in class.
Yeah.
And so as soon as it really became clear that there was an eruption going to happen, it was very exciting. But for me, it wasn't really real until the lava started coming out of the ground, and we saw the first images from the helicopter, and I was like, oh, wait, that is 45 minutes away. Oh my God. I can just go there.
You could just.
I
Can you just walk there? Like, is that?
Yeah, you can just walk there. I mean, in the initial stages of the eruption, the area is cordoned off by civil protection in Iceland, but pretty quickly, they relax these. They want to make sure that people aren't gonna go and like get buried in lava. They want to make sure the situation is kind of stable.
Mm-hmm.
And so it was like fucking magnetic.
Yeah.
As soon as I had the opportunity to, I knew that this is exactly what I needed to be doing. Every single thing was pointing me towards that eruption. I dropped every single goddamn thing that I was doing scientifically and went straight for that eruption because, I studied the mantle, and in Iceland I had started studying kind of these deep magmatic processes and mantle, mantle heterogeneities, we call them. And this eruption was pointing towards, we very quickly got samples delivered to us within hours of the eruption starting, and we processed and analyzed the samples, and the early results of the chemistry told us that this was something crazy, that this was something coming up from very deep. And we needed to really pay attention. And one of the really frustrating things is there was no plan. This is sort of common in Iceland, but there's a reason for it. It's because there is a plan. You're just not a part of it. But we were a research group that was dedicated to studying these kinds of things. And so within my group, I kind of told everybody, maybe there's no plan, but I personally am going to sample this volcano. I am going. I will take, anybody can come, but we're going to get samples, kind of political ramifications be damned. And these early samples, the reason for this is we were reliant on people going to sample that weren't very forthright with giving us samples. And so this would really hamper our ability to do any science and put all of the there's a lot of competitiveness in science. And so there was another researcher that does a lot of the sampling, but he typically doesn't distribute samples. He typically mails them out to his collaborators around the world, which is fine. Every science, science that in that strategy, science gets done very rapidly, and it's not ethically, bad in any way. It's just that we wanted to work on the on the eruption as well, and we have our own perspective on things. And so I jumped in. I went to go get the samples. I got a group of people, and showing up at the eruption was just incredible. I was decked out in all this equipment to kind of keep me safe, and which I had never put on before. And I was scooping up lava with a rock hammer and quenching it, which I had learned how to do, in the day before. And so, but it turned out that this was all pretty easy. And fortunately for everyone, the eruption was very safe. It was a very small eruption and kind of like this perfect little laboratory for scientists to play around and for tourists to kind of hang out. That's what it turned out to be. It wasn't dangerous. And so, or there wasn't a significant volcanic hazard associated with it. And this hasn't been true for most eruptions in Iceland. Volcanic eruptions are extremely dangerous. But this is one of the reasons why nobody had died. There have been 3 eruptions at Fagradalsfjall, and nobody has died. People have gotten injured, but largely it's the injuries are they get lost in the fog, and then people have to go find them. It's not necessarily eruption related. So in any case, I guess I'm going on a bit of a tangent, but
No, go on all the tangents you would like. Yeah, the whole point.
But yeah, Fagradalsfjall was kind of this watershed moment because it made real all of these things that I had studied in this abstract capacity. And it was an opportunity for me to go and study something in reality that was very important and had global attention and was in my backyard. And the significance of the eruption was kind of within the bounds of my scientific speciality. And this is the first time this kind of thing had happened in hundreds of years. So I'm probably one of the luckiest people in the world at that particular moment. I really won the lottery with this eruption. I really happened to be in the right place at the right time.
When you say something like this hasn't happened for hundreds of years, do you mean an eruption or like an eruption like the one that was
Yeah,
happening?
so what I mean is that the Reykjanes Peninsula, which is where the eruptions take place, erupts in kind of a cyclic eruptive behavior.
Okay.
So eruptions occur every 1,000-ish years in periods lasting a couple hundred years long. And we were due, but there's no reason why it can't wait 50 years, in which case you're already retired. And of course, happening at the exact moment you are living in Iceland. As a foreigner, it's an amazing stroke of luck to be there at this very critical time. And so it was fantastic. I remember in the beginning of the eruption, there were two old, super veteran geophysicists who have studied so many volcanic eruptions in Iceland. Bryndis Brandsdottir comes to mind. Bryndis is a super veteran, volcano geophysicist. She's involved not just even with volcanoes, she's involved with everything seismology Iceland. She's really amazing. And she started her career in the Krapla fires in the 70s. And now it's, I guess, 50 years later. And so she's now at the end of her career. And she was telling Páll Einarsson, who is another, emeritus professor at the university. They're both, these people who have been in the same department for decades, studying all the eruptions. He was telling him, Páll, I can't believe we lived long enough to see an eruption on the Reykjanes. The Reykjanes is a locality where nobody really expected to see any eruptions. I mean, they hadn't been there for hundreds of years. In contrast, we have eruptions in central Iceland like every few years. The last time there was an eruption in central Iceland was 2015. So it's pretty regular.
Yep.
Before that, 2010, or even 2011, maybe Grímsvötn, I can't remember. But pretty regular eruptions. So, that's every few years versus every few hundred years. So people were really surprised. And of course, it presented a just enormous opportunity. I won't go into detail about it, but the basalts on the Reykjanes have compositions that are unusually good for studying the mantle. And so this was just an incredible opportunity for me and my collaborators, because we kind of do exactly that. We use lavas with these primitive mantle-like near mantle compositions to study the mantle. And we're having it erupt right here. So our strategy became kind of, we just collect samples all the time from the volcano. And that really paid off, because we saw really crazy chemical changes over time, which is very unusual for volcanoes. Yep. It's usually a single eruption will kind of stick to a similar magma composition. And so we really got to see some really unique stuff.
I do want to ask a bit of a more technical geology question, because I'm genuinely curious.
Yeah.
Those mantle rocks and mantle, I guess, minerals coming up, are they already crystallized when they're being shot out of the volcano, or are they liquid as well with the lava, and then they're crystallizing when they reach the surface?
So mantle peridotite always come out mostly solid.
Okay.
And it depends on the type of volcano, whether they come out completely solid or a little molten. When I looked at mantle xenoliths in the U.S. for my PhD, they were coming out completely solid. They were mantle xenoliths erupting at only a few hundred degrees Celsius. So in reference to kind of give some context to that for your listeners, they're erupting at about 500 degrees, and lavas are 1,200 degrees. So what is that? That's like 700 degrees hotter than. It's way, 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 way hotter. So.
Yeah.
So yeah, so solid usually.
Mm-hmm. Um, so, as a volcanologist who lived and worked in Iceland, could you explain a little bit what exactly is going on in? I hope I don't butcher the pronunciation, but Grindavik.
Yeah, no, it's
Uh,
Grindavik, or
okay,
it's like Grindavik.
Grindavik.
Yeah,
Okay.
yeah, yeah. It has there's an I with an accent, and it's pronounced like ye. Or
Mm-hmm.
actually, higher. It's like ye. I can't. My Icelandic pronunciation isn't actually that good. It's good for, you know, people who aren't Icelandic. But,
Mm-hmm.
so sorry. What was the question again?
So there's eruptive activity happening there right
Yeah.
now, from what I believe. Right. What could are you able to explain kind of what's happening there and
Sure.
why we're seeing what we're seeing?
Sure. Sure. So so the first signs that the Reykjanes Peninsula were becoming active again for the first few hundred after since medieval times um, was inflation, which means that the ground is swelling
Mm-hmm.
and rising. So inflation was occurring in 2022 near Svartsvengi, which is near Grindavik, just north of Grindavik. There's a power plant there. The Blue Lagoon, your listeners might know the Blue Lagoon, which is kind of like a tourist hot spring kind of thing.
Yeah, it's like an hour drive outside of Reykjavik, right?
Yeah, exactly. So there were these inflation events, and the inflation events were connected to magma or gas being injected into the crust at depth. And following that, there were 6 more of these events, culminating. The final one was most recently. So starting in early, I believe it was late October, we started having, or later mid-October, we started having quite rapid inflation, more faster than had been in the past. So the speed of inflation is related to how fast you're injecting magma into the crust. And this can be bad. If it's going really fast, you're injecting a lot. And so
When you
the
say
chances,
injecting, it's like coming up from the mantle. And
exactly.
Okay.
Yeah, so it's coming up from somewhere. Maybe the lower crust, but maybe the mantle. So and injecting is the word because you have this kind of like tube essentially, and the tube comes up or dike planar. The exact geometry of it isn't really important, but you are transporting magma up from depth, and it's forming some kind of body in the crust. So they called it an injection, and so anyway, the magma was coming up at great rate, which is worrying. And it was causing some very large earthquakes. Now, the earthquakes aren't related. It's kind of weird to think about, but it's not related to the magma. It's related, the fact that we have earthquakes is related to stress already present in the crust. And the magma will go in and allow these faults to move and relieve the stress. So it's not, there was a lot of earthquakes, but it's not necessarily connected to the severity of the situation. It's connected to how much stress is built up in the crust. And the magma was injecting itself right into the plate boundary, essentially. And so a lot of stress. And but the earthquakes are very are scary, and they were scaring people, and so it kind of became a media frenzy. And it came to a head when so up until that point, we were seeing the injection of a body that is parallel to the ground, so it's kind of a flat-lying platey intrusion. And when it's in that geometry, it can't really make its way to the crust in an obvious way, because if you put in more melt, then it kind of just gets wider. It doesn't come up to the surface. It just kind of grows in place at depth. But what happened next was more worrying. All of a sudden, a huge dike, which is another one of these planar intrusions, but now it's oriented perpendicular to the ground. So So if you put melt into a dike, it can come up to the surface, if that makes some kind of sense, right? If you extend the dike, it will intersect with the surface. If you extend a sill, if you extend one of these planar intrusions, it runs parallel to the surface, so it wouldn't come up.
Could you just explain planar intrusions one more time? I might have missed that.
Sure. So there are two types. There's sills and dikes.
Okay.
Sills, they have they have the same shape. It's just that sills are parallel to the ground and dikes are perpendicular to the ground.
So these are intrusions of magma, and one is moving kind of like this, and one is...
Yeah, it's the shape. So one is, they're both planar, so they both form these sheets.
Yeah.
But in a sill, the sheet is parallel to the ground. So as you put in more lava, the sheet will kind of extend laterally parallel to the ground. It doesn't come up to the surface.
Yeah.
But in the case of a dike, this sheet is perpendicular to the ground. So as you extend the sheet, it can grow laterally, but it can also grow up to the surface. If the dike extends to the surface, then you have a volcanic eruption. So the dike that was injected at this time was huge. It was much larger than the dikes that had previously been injected into the crust during the Fagerdalsfjall eruptions. And so people were really scared and worried at this moment. And it was at this point, this was like November 10th, when they decided to evacuate Grindavik. And they should have evacuated. This is a very good call. It was a smart call. We could have had an eruption quickly, potentially. But this was, a lot of the thinking was based off of what we had seen in other diking events. But to me personally, it was different because we had both a sill and a dike. The kind of like the subsurface state of the system was complicated, right? You had all these parts, and so there's no reason to expect that things will kind of proceed in the same manner. So there were some people who were immediately saying, we're going to have an eruption in the next hours. We need to immediately mobilize civil protection to go in and get ready to start saving the town and saving the power plant and saving Blue Lagoon. And of course, nothing happened, is what ended up happening. And over time, activity along the dike stopped. Within the first few days, magma's really hot, and so it will cool off quickly. And so after a few days, most of the dike will have cooled and is now solid. So after a few days, it started becoming, there was still a lot of cracking and seismic noise along the dike, which was worrying. But the volcanic threat began to decrease, and there were still people who were saying, we're going to have an eruption any second now. To me, this is fairly irresponsible scientific behavior. I think that we need to really play as a team and kind of come to consensus. There's a lot of different types of data that needs to be integrated. I mean, at this time, I wasn't even living in Iceland. I was living in Germany, and all I needed to do to stay appraised is kind of tune into these meetings of scientists where all these different scientists would present their viewpoints, and you could really aggregate together a really, really clear picture of what everybody knew about the eruption. And at these meetings, kind of the group would come to a consensus about what was going on. And the consensus during a lot of the time is an eruption may happen. It is not guaranteed to happen. And the most likely location of eruption is not in Grindavik. And so I think particularly as time went on and the volcanic threat decreased, the memory of these people who, I don't think the people who said, oh, there's going to be an eruption any second now, ever really walked back their comments. It was kind of buried in more, the news cycle's pretty short. So, but, we all remember as scientists. And I think there's a lesson here for the media where, there's different sources that you can draw from. And the media will naturally go towards nice punchlines, things that will get clicks on their articles. I mean, that's just kind of the state of the world. And as media consumers, we need to always remember that.
Just a small disclaimer, There's going to be some siren sounds for the next couple seconds. You are not going crazy. There were some police sirens outside of my hotel room in San Francisco while I was recording this for just like 10 or 15 seconds.
There was kind of a scientific consensus from responsible scientists, and then there were kind of, I don't want to call them fringe scientists, but there were other scientists who kind of operating outside of the consensus and forming their own viewpoints, which isn't wrong, of course. Everybody's entitled to their own opinion, but typically the conclusions they came to were less conservative, I would say, and so this was a point of frustration. Anyway, since that point, there hasn't been a whole lot of activity in Grindavik. There's been continued, the dike has essentially gone quiet at this point, and there's continued inflation in like before, but it's very much slowed down. So it's seeming at this point, unless something changes, that there will not be an eruption in Grindavik. And this is a very good thing, of course. There's a huge difference between the eruptions at Fagradalsfjall, in which there is nothing at Fagradalsfjall. It was it was an old sheep farm. And in the end, nothing, I don't believe anything was destroyed, no fields or anything. So that was an amazing, fortunate stroke of luck for everyone involved. Whereas in Grindavik, there's a power plant, there's Blue Lagoon, there's a city, there's roads that connect the island together. It would have been a true disaster. So it's really, really fortunate that that there was no eruption. Yeah.
What would you recommend to someone living in Iceland, or maybe that just wants to keep up with volcanology, that wants to avoid a kind of like almost media biased, like very what's the right word? Just like overreaction to the events that's happening. They want to like that respectable scientist opinion.
There is a entity within Iceland called the Icelandic Meteorological Office, and although it's the meteorological office, it's kind of like the more formal volcano monitoring center for Iceland, and they really represent. They're led by this woman, Katrín Jónsdóttir. She is very good, and she is totally connected to everybody. Yeah. And they kind of lead the consensus, and they put out very frequent when we have these kinds of volcanic crises, they post out messages to everyone and keep everybody updated, and they kind of have this blog. You just need to go look at this website. It's very easy. It's very understandable for the lay public. They're really good at communicating. Yeah. I think the unfortunate part of it is it's not like media in people's face. It's just a blog on the website of a random government,
not
entity.
super fun to watch and scroll through,
No way. They don't have, they have pretty cool maps, but it's a bit technical. They certainly don't have like an exciting YouTuber or something like helping to communicate what's going on. It's like reading the weather. It's not very inspired.
Volcanic weather,
yeah. But or updates on what's happening. It's certainly not entertainment news, but it is the most accurate and best information, and they do a really, really excellent job of getting all the information in one place and getting the most important information, and then really informing people. So I have kind of like the inside access in some ways. I don't have the closest inside access, but I have kind of like an inside scientific access, and they are pretty much keeping up with me. They're like maybe a little behind, maybe by, just because of updating probably. They actually have to write out an update, so it takes them a little time to do that. But they're basically figuring things out as fast as the scientists.
But the information is very biased or unbiased
very
and
accurate.
Yeah,
it's very accurate information.
Okay.
Yeah.
You mentioned earlier that in the 2021 eruption, I don't even want to try pronouncing the name, but the 2021 eruption.
Fagradalsfjall.
Fagradalsfjall.
Yeah.
In that eruption, magma was coming up from really deep within the subsurface.
Correct.
Is that something that's unique to that area? Like why is magma coming up from so deep?
That's a great question. We don't really know. That's actually one of the things that I am studying in my work.
Mm-hmm.
I think why is magma coming up? Fagradalsfjall is really unusual even within the Reykjanes. So I said earlier that there hadn't been an eruption on the Reykjanes in hundreds of years since medieval times. Well, there hadn't been an eruption at Fagradalsfjall for more like 6,000 years.
Mm-hmm.
Eruptions occur there very rarely. And the magma compositions that are up there are very unusual. And what's likely happening is that the Fagradalsfjall has a deep connection. So different eruptions are sourced at different depths. Usually they're sourced within the crust, often the middle crust. And Fagradalsfjall seems to be sourced from the base of the crust, so all the way at the bottom, essentially in contact with the mantle. And this is very unusual. This is the first time we've ever seen this in Iceland, and it's pretty unprecedented worldwide as well. And so one of the scientific opportunities here is that we get to study what happens to magmas at depth. What are they doing down there? I mean, we have ideas. We've inferred it over decades of study, but we've never been able to directly observe it like we can in that eruption. So that's one of the really interesting things that this eruption presents. Yeah.
How do you capture mantle rocks and those crystals from the mantle that you were mentioning? If it's being sourced from the lower crust, is there material from the mantle that's moving up, or?
Yeah, the lava.
Gotcha.
So the lava comes from the mantle. So we study the lava composition.
Okay.
There's no actual chunks of the mantle coming up. Nobody has ever found a piece of the mantle that's come up in Iceland.
Mm-hmm.
At other places around the world, you can find it. So, for example, where people find diamonds in kimberlites and lamperites and things like that, these are bringing up rocks from incredible depth, and they bear xenoliths. They bear these mantle chunks. But in Iceland, magmas are stored at depth, are stored above the mantle before eruption, basically always.
Mm-hmm.
And so this means that the mantle xenoliths, because they're large and dense, they fall to the bottom of the magma. They sink quickly to the bottom of the magma chamber. And so because of that, you don't get any mantle xenoliths at all.
Gotcha.
Which is a huge bummer, but that's life. Yeah.
So, from what I understand, you use a mass spectrometer pretty
Correct.
often to analyze the samples that you gain in the field. What makes that machine so useful, and what would be a good definition of that for someone who's not super familiar with what it does and geochemistry and things like that?
So yes. So a big line of research that I do is isotope geochemistry, and this is what mass spectrometers specialize in. But a mass spectrometer is simply an instrument which you put in a sample, usually in liquid form, actually they make mass spectrometers where you can put in solid, liquid, or gas forms. But in any case, you take your sample and convert it to ions, and the ions are accelerated in the mass spectrometer, and then there is what we call there's the spectrometer part of it. So the ions are sorted by mass, and when you sort them by mass, you can sort out the different isotopes and elements involved. So, for example, one commonly used isotope system are lead isotopes. So there are 4 lead isotopes: lead-208, lead-207, lead-206, and lead-204. And when you feed the lead into it, it splits the lead that's input into it into 4 beams of ions, each corresponding to a different lead isotope. And then by collecting these beams in detectors, 4 different detectors at the other end, and seeing the difference in signal, you can look at the variation, or you can directly measure the ratio of abundance of one isotope to another isotope. Mm-hmm. And the reason why you do this is because that ratio is controlled by things like radioactive decay or various magmatic or chemical processes. And so by using isotopes, we can figure out and kind of infer the history and processes that have affected the material that we're measuring the isotopes in, if that makes some kind of sense.
No, yeah, that definitely makes sense. Are there radioactive, I mean, you mentioned radioactive decay. Are there radioactive elements coming up in volcanic eruptions?
Oh, yeah, not just in volcanic eruptions. Radioactive elements are everywhere. I mean, potassium is radioactive, so bananas are quite radioactive, actually. But the important, the commonly, so often we look at, there are a bunch of these radiogenic systems that we use in isotope geochemistry. So things like the samarium-neodymium system, the rubidium-strontium system, the uranium-lead system. All of these systems are not just used like I use them. So you measure the isotope composition, which is what we call it when we make one of these isotope measurements. But you can also use them for as a radioactive decay dating clock. You know, you can use like uranium, lead, and a zircon to date that zircon, because uranium decays to lead. You can go in and look at the lead isotopic composition, and that will change very systematically over time. And so if you go in and you see a particular lead isotope composition, that actually corresponds to a particular age, which makes it a very powerful system.
And what is age exactly telling you about the sample that you're looking at? Like the age of the magma itself, or the lava?
So I was talking about radioactive systems in kind of broad strokes. In lavas, we don't do so much dating with uranium lead.
Yeah.
You can do other kinds of dating like potassium argon or argon argon dating, which is based on the decay of potassium to argon. And this is because when a lava flows over the surface, all of the argon in the lava comes out. And so all you have is potassium. And so as the potassium decays to argon, you can use this as a clock. So you take the sample, you measure the amount of argon and sort of the amount of potassium. Argon's a little complicated to explain right now. But you can work out the age based on the amount of argon that has decayed in the sample. So that's an example of how you might date a lava. But I don't do so much dating. I use isotopes to figure out where lavas come from, because when a lava forms, it forms from particular materials deep in the mantle that are unknown, and these materials give it particular isotope compositions, so a particular value. And when we measure it up on the surface, we can infer what the lava formed from by its isotope composition. So this is really powerful. You know, there are lots of different processes that affect the composition of lavas. You know, fractional crystallization. I don't know. Assimilation. You know, gathering. You know, absorbing materials in its environment. And isotopes are really good at seeing through or being able to kind of see all of the different processes that are happening in this system. And so they're just unbelievable tools to unraveling all the different things, not only where the magma comes from, but then all the things that happen to it on the way to the surface. So this is why mass spectrometers are so powerful, is that mass spectrometers allow us to peer into this world that is very powerful in its ability to kind of see deeply into what has happened, where the lava has come from and what has happened to it.
And you mentioned that, or the other day when we met, you mentioned that the geochemical techniques that you use give you kind of a broader sense for the kind of the history of that magma and lava, more so than geophysical techniques. Is that something to quote you on, or?
Yeah, no, you can quote me on that. It's geophysical techniques and geochemical techniques are very different, and they have totally different senses. So geochemistry cannot say almost anything about the shape of a lava body, or with difficulty it can say kind of like where it is located before it erupted. It can't tell you what is happening in the system before eruption, right? You can't do anything with geochemistry until the lava's come out of the ground.
Mm-hmm.
So geochemistry in some ways, and some people do kind of feel this way, the geochemistry is kind of useless from a volcano monitoring perspective, because, let's say you get a geophysicist, a geochemist in the room, and they're wondering about Grindavik.
Mm-hmm.
The geophysicist will have a lot to say, and the geochemist will say, well, we got to wait until the eruption happens. And of course, everybody in charge is going to be pretty upset with the geochemist, because the whole meeting is about whether it will erupt or not. So this is so the thing that's really powerful about geochemistry is that after the fact, and it doesn't matter when, we can study lavas that are billions of years old. After the fact, geochemists can go in and use many different elements and isotope systems to reconstruct what happened to the lava, where it is, what melts combined to form it, what types of things were going on in the magma storage reservoir system, in the deeper plumbing system. And geophysics can have some trouble with thinking about this, because magma bodies can be difficult to detect in the crust. Magma bodies can be quite thin, and when things are thin, they may be smaller than the wavelength of seismic waves, for example. And so everything becomes very blurry.
Yeah.
They can detect, geophysics is very successful at detecting broadly that, there is magma or fluid or something at depth. There's something down there, but it's hard for geophysics to be really specific. That said, it's also difficult for geochemistry to be really specific. Sometimes the types of tools that we have for assessing the depth of a magma body, for example, is a lot less precise than the tools that geophysicists have.
Yeah.
But we know exactly it's within a particular range. So what's really powerful is to combine the two techniques together, because then you can create really consistent you can create really consistent images of what is happening within a particular volcanic system, which is, consistency is king. I mean,
Yeah, it kind of reminds me, or geophysicists almost seem like the on-the-ground detectives, interviewing you in the interrogation room. They're on there and they're trying to figure out like kind of a broad scale, or I don't want to say broad scale, because geochemistry gives you a very broad scale. But you guys are more like the forensic scientists, and something's already happened, and then you're using that chemical history to kind of tell you about.
I think that's a pretty correct way to do it. The geophysicists are kind of like working, they're out there, they're really trying to like fight the crime as it's happening, this kind of thing. Whereas the forensic scientists, as things are, they get the most important cases to kind of like look at after the fact, and they build these very detailed court cases. That's really kind of how it works. One of the frustrating things for some people about geochemistry is that data collection can take a really long time. So we just, although the 2021 eruption finished in September of 2021, we actually only recently finished collecting all the data from the eruption, and this is actually unusual. It's been an unusually long time, but it's just an example of how slow geochemistry can be. In contrast, if you put out your seismometers, you are collecting the data as it's coming out. If you miss an earthquake, it's gone, right?
Yeah.
You can't go back. But in isotope geochemistry, you have a physical rock sample, so you can absolutely go and analyze it whenever you want.
Mm-hmm.
So it's never really lost unless you lose the rock sample.
So where is the field of volcanology headed? You know, like, does the volcanologist of the future look like someone who tries to incorporate, you know, geochemistry and geophysics, or is it kind of branching out into its own respective fields?
So I don't consider myself a volcanologist, so I'm not a very good person to ask on this topic. But in terms of geochemistry, I think one of the really exciting futures is kind of continuing to develop these tools where you can calculate pressure, where you can calculate temperature, and where you can use tiny trapped blobs of melt in crystals to figure out what's happening much deeper in the reservoir. There's a lot of really exciting tools being developed in geochemistry using what we call in situ techniques, where you're measuring just a tiny spot in a crystal or something. And so in doing this, for example, if you have a crystal that grows and you have this kind of like tree ring-like growth pattern within the crystal, you can really get in there and figure out all the different things that happen as the crystal grew.
In rings.
Sometimes, yeah, they
That's
can
really
do
cool.
that. Yeah, so the crystal kind of grows outward and it forms these annually, just like a tree.
Wow.
Yeah,
And so this is like very slow crystallization, and then every couple years or every year it forms a ring?
not necessarily exactly like a tree.
Okay.
But you know, you might the magma chamber might be cooling, or there might be injections of melt, and this will cause these kind of like episodic growth episodes. And so you can go in and kind of track the growth of the crystal this way. But
Okay.
it's not necessarily regular like a tree. And unlike a tree, crystals can resorb. They can begin to be dissolved back into the melt. So crystal growth can be very, very complicated, unfortunately. Yeah. But sometimes it's simple, and you can go in and measure, you know, just as you might imagine, measure the different growth rings of a tree.
How would you get around, you know, like types of crystal deformation and pressure solution and things that are going to deform the crystal that you're looking at and kind of change its chemistry?
So crystal deformation is desirable for some people. Some people study deformation in particular. Depending upon the context, the crystal won't deform. When you're deforming a crystal, it has to be kind of locked in with other crystals. You know, if it's free floating in a magma, how is it going to be deformed? You know, if you squish it sideways, well, all the melt squishes. The crystal doesn't squish. It's much harder than the melt. So you have to take the crystal and trap it in something rigid. And so this is something that people have been looking at is these kinds of deformations and looking at, if you have a big thick pile of crystals, how is this pile of crystals going to, you know, sitting at the bottom of the magma chamber. So we can imagine, so for some context, we can imagine just like a big spherical magma chamber, and the magma is crystallizing crystals, and the crystals fall to the bottom of the magma chamber. So you build up a big kind of like, you know, snow pile of crystals at the bottom. Well, you could have deformation within the snow pile over time, and this will cause, you know, deformation of the crystals. But by looking at the crystals, you can work out exactly what's going on in the snow pile. And this is something that is kind of a growing field of study, although I don't personally do it.
Gotcha.
Yeah.
And in the mantle rocks and crystals that are coming up to the surface that you're analyzing, does the heat of a volcanic eruption deform them or change them in any way, or is it already too hot in the mantle that they're just cooling down as they come up?
No, yeah, they're just cooling down as they come up generally. Gotcha. Usually the crystals coming up, at least in Iceland, the crystals coming up are almost always formed at higher temperatures than the melts they reside in.
Gotcha.
So,
which is why they're solid as they're coming up.
Yeah. But it's not quite it's not always so clear cut.
Mm-hmm.
Um, what you're essentially trying to say is, what is controlling is temperature, just temperature controlling crystal stability. If you have a crystal and you heat it up, if you heat it up really hot, it will melt. But there are other things that control this crystal stability, pressure being one, volatile content being one. And so it's a bit more complicated than just temperature.
What exactly is volatile?
Volatiles are things like water and CO2 that are dissolved in the melt. And what it's turned out over the past few decades is that this volatile content, the water content of a melt or the CO2 content of a melt, really affects the chemical properties of a melt. It's very important to take that into account.
Yeah.
So if a melt is very water rich, the crystals will have a different composition than if it's water poor. Degassing, that is the loss of volatiles out of a melt, will affect its chemical properties and even its physical properties.
Gotcha.
Yeah.
And I already kind of know the question, or kind of know the answer to this question, but for the listeners, especially people who aren't super familiar with geochemistry and volcanology and things, what chemically, with the magma and lava on Iceland, creates these kind of slow-flowing, I don't want to say safe eruptions, but it's definitely not a Mount St. Helens or a Krakatoa or anything like that,
Sure. So I guess what you're talking about is kind of like the explosivity of the eruption. The explosivity of an eruption is related to the composition and well, I guess composition is a bit too all-encompassing. It's related to the viscosity and volatile content of the melt. So the reason why melts kind of explode when they come to the surface is because, or some of them, not all of them. At Fagradalsfjall, no explosions. You can imagine there's a melt that is like a glass practically. Highly silica-rich melts are very glass-like, extremely viscous, very difficult for them to flow. And if they come up to the surface, and these melts typically have very high volatile content, so there's a lot of water often dissolved into the melt. So as they come up to the surface, it's the exact same process as shaking up a soda bottle and then opening it. The gas starts coming out. Except in the case of rocks, there's really a tremendous amount of gas dissolved inside the lava, and they're at unbelievably high pressure. So a soda bottle is not at very high pressure. But magmas are under such immense pressure that when they come to the surface, the pressure release is so great that it explodes essentially. They begin to form bubbles, and the bubbles grow and grow and grow and grow, and the rate of expansion is so rapid that it's essentially explosive.
Yeah.
So this is why some eruptions behave the way they are, or behave explosively like that. In other contexts, like at Fagradalsfjall, you don't have explosive eruptions, and this is because at Fagradalsfjall, the lavas aren't viscous. They're very, very runny and very fluid, and there's not a lot of gas dissolved into them. There's some gas, certainly. They form huge bubbles and things, but a lot less than some of these highly silicic lavas, with a lot of water dissolved into them. So at Fagradalsfjall, what happens instead is the lava is coming up, and it kind of turns into a foam. And the bubbles might come together and form big bubbles, but that's basically all that happens.
So like a foam, like there's that much gas. Wow.
Yeah. Like really a foam. And so we see behavior at Fagradalsfjall like forming these beautiful tall jets. And why this happens is a bit complicated. In fact, it wasn't really understood. There's a recent paper out that thinks a lot about how these jets might form. But how they form is pretty tricky to explain. So, but the important thing to think about is some eruptions like explode when the magma comes up to the surface. And Fagradalsfjall had like kind of a lava lake intermittently. So lava immediately at the surface, just sitting there. So that's a really big difference from lava coming to the surface and exploding. Yeah, so that kind of maybe gives you a sense, there's a difference in composition, a difference in viscosity, difference in volatile content.
Yep.
That causes the different behavior.
Yeah. Thank you so much for coming on. I really, really appreciate it. Thank you for taking the time to come out here. I, at the end, want to give you the floor to promote anything that you got going on, or if people want to learn more about your research or learn more about you, where can they find you? Anything like that.
Yeah, sure. Thanks for having me on, Jason. I don't have as much of an internet presence as I'd like, but if people are interested in contacting me or anything, I have a profile up on the University of Iceland website. If they just Google me, like Edward Marshall Geology, I'm like the full first page of Google results. So I'm a pretty easy guy to find. Yeah, I got some cool research coming out. We have a paper out in Nature about the Fagerholmsfjall eruption, but we have a bigger, much more complete paper that'll be coming out hopefully early next year. So keep an eye out for that. Then we'll really have the story about the eruption, which will be nice.
Sounds good.
Thank you very much for tuning in to the third episode of the Heights of Humanity podcast. This episode was a blast to film, and I'd like to sincerely thank Dr. Marshall for coming on the show at such short notice. If you want to find out more about Dr. Marshall, you can simply Google his name along with geoscience at the end. You can also find him on Twitter, also known as X, at Tetrahedra. That's TETRAHEEDRA. Be sure to check out the Heights of Humanity YouTube channel and social media. We're on Instagram, Twitter, YouTube, and almost all major podcast streaming platforms. Just type in Heights of Humanity podcast. You can also check out our official website at www.heightsofhumanitypodcast.com. As always, thank you so much for tuning in. See you in the next episode.